Hello everybody, my name is Ronald Jung. I'm a PhD candidate at the University of Klagenfurt and I'm supervised by Professor Weiss. In this presentation, we demonstrate the capabilities of a state-of-the-art distributed collaborative state estimation approach in the context of reliable autonomous navigation in swarms of communicating robots. Since this workshop aims for reliable sensor technologies in industry as well as in the mobile robotics sector, we want to present desirable properties of collaborative state estimation, such as sensor sharing or indirect sensor relaying, and how it allows for redundancy in a global scale if local sensors on individual robots fail. Another nice property is that less accurate robots directly benefit from more accurate ones. First of all, I want to give you some background information and explain you our primary motivation. A team of n collaborating agents has potentially many applications, and an accurate localization estimate is a prerequisite. Typically, each agent runs locally a filter that treats states as multivariate random variables, which are propagated by proprioceptive sensors and are corrected by exteroceptive ones. Now the question arises, how to incorporate n distributed estimators correctly? Collaborative state estimation aims to fuse information provided by different sensors from all agents in a statistically optimal fashion, meaning that the information provided from different sensors from all agents have to be considered. This can significantly improve the estimation performance of correlated agents, provide redundancy in case of sensor failures, and less accurate agents benefit from more accurate agents. Thus, this is often used in the field of collective localization. In a centralized fusion architecture, a lot of communication is needed. Research in the past decades has shown that rendering collaborative state estimation distributed is challenging, as it can degrade the performance, lead to inconsistent estimates, requires extensive bookkeeping or communication. It becomes even more challenging if agent uses a sensor that provides measurements at high rates. In our case, we use an IMU, a state propagation sensor, which typically provides measurements at a rate greater 100 Hz. In collaborative state estimation, we can distinguish between three different filter steps. The state propagation step is advancing the estimate in time, based for instance on a control input, encoders or an IMU. Private observations are correcting estimates based on local exteroceptive sensor readings, for instance a GPS measurement, and joint observations are referring sensor readings directly or indirectly to multiple agents' estimates. Those can be various relative sensor measurements between agents, for instance range bearing, relative pose, etc. Initially, agent states are independent, shown by zero entries in the off-diagonal blocks of the joint covariance matrix. Joint observations lead to coupling, and estimates become more and more directly or indirectly correlated. Covariances are positive semi-definite. Thus, upper and lower triangle matrix contain the same information. Homoeotis and Bakey propose to factorize cross-coverances, which allows each agent to perform the state propagation distributed and exact, as emphasized by those orange rectangles. Therefore, we call this strategy distributed propagation. Nonetheless, update requires still the global state and a persistent all-to-all communication. Persistent communication is a challenging constraint and should be avoided if possible. Therefore, Luft et al. Proposed approximations for the filter update steps that allows isolated private and joint observations by neglecting non-participating agents. We call this strategy distributed approximated CrossCoverance. This example shows a joint observation between agent 1 and agent 2, while technically any number of agents can participate. The joint covariance of participants, held in blue, can be restored exactly, but the cross-covariance terms of non-participants in the purple square have to be corrected by an approximated factor. Globally seen, This leads to conservative estimates, but communication is only required at the moment of joint observations. Unfortunately, maintenance of all cross-currents is still needed locally for each filter step. That's the state propagation step, private observation, and joint observation, which increases linearly with the number of known agents. To overcome this burden, we proposed recently to use a single buffer per agent containing correction terms for all factorized cross-currences. This strategy is called distributed approximated history. For each filter step, we identified correction terms. For the filter propagation step, it is the state transition matrix phi. For private and joint observations, each agent applies a correction in relation to the gained information. If the buffer size suffices, it allows to significantly reduce the maintenance effort for interdependencies on each agent. In our evaluation, we want to simulate the impact of joint relative position measurements on a swarm of heterogeneous robots. There are two types, aerial and ground robots, both running locally a quaternion-based aerostate extended gamma filter that uses ANMU, a strapped-down state propagation sensor, at a rate of 200 Hz. This makes the pose estimation independent from the underlying kinematic motion model. Each estimator fuses absolute position sensors and relative position observations at the rate of 5 Hz, which stem, for instance, from a range bearing sensor or a camera-based visual tag recognition. We assume that aerial robots have a better signal reception and is equipped with a more accurate sensor, for instance an RTK GPS, providing measurements at 10 Hz, while agents on the ground receive updates at 2 Hz, which suffer from message drops and sensor outages. Finally, we investigate on the processing overhead, performing collaborative state estimation by measuring the total filter execution time on each agent. Please note that the paper provides a table with all simulation parameters. We generated for the aerial robots a takeoff circle land trajectory to have sufficient excitement for the IMU to render the biases nicely observable, as all states were initialized wrongly. The orange lines visualize relative position measurements between aerial and ground robots. For simplicity, those happened at the same moment, but could be technically at different rates and points in time. We define Robot 1 to be the Interim Master to process joint observations. This means that other robots communicate their states to the master and obtain a correction later on. Technically, this processing load can be shared among other robots as well. The processed joint measurement of Robot 1 and Robot 3 can be depicted on a plot, while sensor outages and dropped messages can be clearly seen and are highlighted by the pink ellipse. This figure shows that trajectory is processing relative position measurements or not. Due to the noisy IMU, the estimator starts to diverge if the ground robot suffers from dropped absolute position measurements or sensor outages. This can be omitted by processing relative position updates. To show the effect in more details, the error and uncertainty of estimated position Robot 3 is shown. It can be seen that the uncertainty increases slightly if local absolute position measurements are missing, but relative position updates are performed. As soon as local observations were obtained, the error and the uncertainty decreased again. The error remains bounded, and an average RMSE of 0.1 meter was achieved. While having no relative observations, the error grows unbounded and an average RMSE of roughly 0.7 meter was achieved. We saw that the accuracy was improved, but at which cost? Due to the made simplifications, all joint observations were performed on Robot 1. In total, all joint observations made up 4.4 seconds and caused an increase of approximately 58%. Those remarkable spikes in the propagation step stem from the forward propagation of cross-currents to prevent them to fall outside the buffer horizon. For further details, one can find a table in the paper regarding the filter performance and execution times. Summarized, the evaluation has shown that collaborative state estimation can be used to provide redundancy, especially if the local census view does not. It improves the estimation at the cost of increased processing time, and it paves the way for new possibilities and applications, for instance in exploration tasks or for communicating smart cars, etc. We found similarities between collaborative state estimation and multi-sensor fusion and demonstrated that approaches from collaborative state estimation can be used in the context of multi-sensor fusion, having superior advantages over state-of-the-art approaches regarding scalability, modularity, and compute complexity. We are now aiming for a demonstrator for modular and tightly coupled ultra-wideband and differential barometric fusion. Further, we want to perform real-world experiments on multiple drones in autumn. Thank you for your time, and if you have any questions, please direct them either to myself or Professor Weiss.